Welcome to the Deep Dive, the show where we take a stack of your sources, your articles, your research, and yeah, our own pretty extensive notes, and we pull out the really important stuff, those impactful insights just for you.
And today, we're not just dipping our toes in.
No way! We are plunging headfirst into one of the universe's most, well, mind-bending, gravity-warping mysteries, black holes.
These things are so extreme, so profoundly bizarre.
That even Albert Einstein, right? The guy who basically wrote the rule book with general relativity, he initially found it almost impossible to believe they could actually physically exist.
Yeah, he really did. He saw them as theoretical oddities.
Yeah.
Mathematical curiosities maybe, but too strange to be real.
But the universe, as it turns out, had far more astonishing plans.
It's a truly humbling thought, isn't it? That Einstein, whose genius gave us the framework, wrestled so much with their reality.
Totally.
His skepticism just highlights how revolutionary the idea was, even for him. It shows the immense challenge, even now, in understanding these extreme environments.
Absolutely, and that's exactly what we're here for, to guide you through this, well, extraordinary landscape. My goal is to navigate these depths with you, making sure you get genuine understanding, not just facts.
Our mission today is to take all this complex research, Nobel Prize stuff, deep dives into quantum gravity, studies of accretion disks, and turn it into clear, compelling insights.
Yeah, we promise surprising facts, those unexpected connections, plenty of aha moments to cut through the noise. You're going to feel really well informed about one of the universe's most exotic phenomena.
We'll cover everything from the basics to how they power galaxies and the huge mysteries they still hold for us. Mysteries challenging the very laws of physics.
And our exploration today, it's not just summaries. We're digging into the real bedrock here.
That's right. Foundational work, complex analyses probing the limits, detailed observations showing these monsters in action. It's a journey from pure math to cosmic engines.
Okay, so let's start right at the theoretical beginning. It's pretty significant, like we said, that Einstein, who developed the theory predicting them, had such a tough time believing they could actually form. Why was he so skeptical?
It's a great question. It really speaks to how radical black holes are. Einstein's issue wasn't the math, really, but the sheer extremity of what general relativity implied.
Meaning?
Well, his equations describe space-time collapsing to a point of infinite density, a place where time itself just stops in any normal sense. This idea of a singularity, a point where all known laws of nature just break down, he found it almost too outlandish.
Too far-fetched to be real.
Exactly. Just a mathematical quirky thought, not something the universe would actually do.
Fascinating. The father of the theory doubting its most extreme child. But then, about a decade after Einstein died, someone else took up the challenge.
Indeed. 1965. A brilliant British mathematician and physicist, Roger Penrose. He used what were called ingenious mathematical methods, specifically topology, to prove definitively that black holes aren't just theoretical weirdness.
He proved there were real consequences.
Yes. He showed they're a direct consequence of general relativity itself. And importantly, he proved they could form stably from collapsing stars, and that the singularity was, well, inevitable under realistic conditions.
So not just a minor tweak, this was monumental.
Absolutely monumental.
Yeah.
Penrose's paper from January 65, it's still seen as maybe the most important contribution to GR since Einstein himself.
Wow.
His work gave us this rigorous concept of the singularity right at the heart of the black hole. Not just extreme density, but a boundary where, like the sources say, all the known laws of nature break down.
A point where physics just stops working.
Pretty much. Our equations go infinite, cause and effect unravels. That's the singularity Penrose showed could actually form.
That's genuinely mind-boggling. And to really grasp this idea of no return, this one-way street, I love that analogy from Subramanian Chandrasekhar.
Oh, the dragonfly one.
Yeah. The larvae underwater promise their friends they'll come back from the surface, but once they transform and fly away, they can't. The ones below never find out what life's like up there.
It's such a vivid way to picture it, isn't it? This profoundly counterintuitive reality. Once matter collapses enough and that trapped surface forms, which Penrose defined rigorously, nothing can stop the collapse.
And that trapped surface is the event horizon.
Precisely, the event horizon. It's a boundary where all paths, even light's path, point inexorably inward towards the singularity. Like the dragonfly, cross that boundary and you're committed. No information, not even light gets back out. The ultimate one-way trip.
A cosmic prison.
Exactly. No escape.
Okay, so we've got this incredible theory, doubted at first, then proven mathematically. But how do we go from theory to observation? A black hole is, well, black. It doesn't shine. How do we know they're out there? What do we look for?
Right, that's where the detective work comes in. And what's fascinating is they are invisible, but their immense gravity leaves undeniable clues. Yeah, we don't see the black hole itself, but we see how its colossal gravity directs the motions of the surrounding stars. Gas, dust. It's like watching an invisible dancer. You only see them by how the other dancers move around them.
Well, the light from stuff falling in.
Exactly. We detect them indirectly by those huge gravitational effects on nearby stuff.
And this isn't just guesswork, right? This led to a Nobel Prize, confirming them pretty definitively.
Precisely. The 2020 Nobel in Physics went partly to Reinhard Genzel and Andrea Ghez for exactly this. They led separate groups working for decades, watching the very center of our own galaxy, the Milky Way.
What did they find?
They found an invisible and extremely heavy object right at the core, controlling the orbits of stars, whipping around incredibly fast and close. The only known explanation for something that massive, millions of times our sun's mass and that compact, is a supermassive black hole.
So confirming Sagittarius A?
Confirming SGRA, yes.
Okay.
The long-suspected black hole lurking right there in our galactic backyard.
That's just incredible, especially given how hard it is to see the galactic center. From here, there are those enormous clouds of interstellar gas and dust blocking most visible light. It's like trying to see through thick fog. How do they manage?
They were pioneers, developed revolutionary techniques. Genzel and Ghez used infrared telescopes and radio technology, which can cut through that gas and dust, letting them see through the galaxy's disk to the core.
And they had to deal with Earth's atmosphere too, right?
Yeah, they used sophisticated adaptive optics to correct for the blurring caused by our turbulent atmosphere. It was this meticulous, long-term work pushing technology to its limits that gave us the most convincing evidence yet. A real triumph, turning theory into confirmed reality.
Okay, so theory proven, observations confirmed. Let's unpack this more. Let's shift from how we found them to the basic properties that actually define a black hole. What are the key features setting them apart?
Right, the absolute key feature is the event horizon. Think of it as a sphere, roughly GMC2 in radius. But crucially, it's not a solid surface you could, land on.
Okay, not solid.
No, the sources are clear. Black holes have no rigid surfaces. That's unique, totally different from neutron stars, which do have a surface. The event horizon is one-way membrane, a boundary where, once you're inside, nothing may emerge, not even light.
So it traps light.
Exactly.
Yeah.
It's sometimes called a null surface, meaning light paths there are trapped. They can't move outwards, only stay put or fall in. Cross that line, your fate is sealed. Straight towards the center.
Sounds terrifying. Cut off completely. But what about rotation? Most things spin, right? So what about spinning black holes?
Yes. For spinning black holes, which we think most are. There's another fascinating, truly bizarre region, the ergosphere. It's outside the event horizon, but inside another boundary called the static limit.
What's special about it?
What's unique is that space-time itself is dragged along by the black hole's rotation.
This
frame dragging means inside the ergosphere, everything, even light, is forced to rotate with the black hole.
Forced. You can't stand still.
You literally can't stand still relative to distant stars. Imagine being caught in this cosmic whirlpool where reality itself is flowing. It's so extreme. And what's really wild is that within the ergosphere, negative energy states are possible for particles relative to someone far away.
Negative energy. That sounds like sci-fi.
It sounds implausible, but it's a consequence of the frame dragging. And it opens the door to potentially extracting energy from the black hole itself. We'll get back to that.
Okay, negative energy states.
Wow.
And then there's a specific limit for stable orbits, right? The ISCO.
Yes, the innermost stable circular orbit, or ISCO. Hugely important for understanding how black holes feed. Our sources define it as the smallest circle, at least RRAMs, along which free particles may stably orbit.
Like a cosmic point of no return for orbiting stuff.
Sort of. Beyond the ISCO, things can orbit stably. But once matter gets to the ISCO radius, which varies depending on the black hole, no stable circular motion is possible. Anything crossing it is doomed to spiral in fast.
And this is purely a relativistic.
Yes, it's a unique feature of relativity. Newtonian gravity allows stable orbits at any distance, theoretically. The ISCO's existence is key observational evidence for strong gravity. We see hints of it in things like X-ray binaries, where the inner disk edge seems stable, maybe linked to this boundary.
All right, we've got the basic features. Let's go deeper into the math descriptions, starting with the simplest possible black hole. What's that one called?
That would be the Schwarzschild solution. It's the most fundamental model. It describes a black hole that's not rotating, has no electric charge, is perfectly spherical, and sits in empty space of vacuum.
The basic model.
Exactly. It's a direct, elegant solution to Einstein's vacuum field equations. Just pure space-time curvature, no matter, or energy involved. It's the baseline black hole.
And this gives us the famous Schwarzschild radius. We hear that term a lot. What does it really mean, practically?
Right, the Schwarzschild radius, RS equal 2gmc2.
Yeah.
So that size the scale where gravity gets so strong that even light can't get out. To make it concrete, if you squish the Earth into a black hole, its Schwarzschild radius would be about a centimeter, like a marble.
Tiny. And the sun?
If the sun collapsed, which it won't, it's not massive enough, its Rs would be about 3 kilometers, the size of a small town.
Wow.
These examples show how tiny relativistic effects usually are in our world. They only dominate at these crazy extreme densities. That's where Newton breaks down and GR takes over, defining space-time itself.
So even our sun would just be 3 kilometers across as a black hole. And this simple Schwarzschild solution is surprisingly powerful, isn't it? There's a theorem about it.
Yes, extremely powerful, thanks to Birkhoff's theorem. This theorem basically says the Schwarzschild solution is the only possible spherically symmetric vacuum solution that looks flat far away.
Okay, what's the big deal about that?
The profound insight is that the space-time outside any collapsing spherical star, even one that's messy and changing inside, must eventually settle down to look exactly like the simple, unchanging Schwarzschild metric from the outside.
So all the internal complexity gets hidden.
Once it collapses past the Schwarzschild radius, yes. The messy details of the collapse become irrelevant to the external spacetime. It's a surprisingly robust result, simplifying things a lot.
That is powerful. What about light near the simple black hole? How bent does it get?
Dramatically bent. Much more than Newton would predict. There's a specific place called the photon sphere at RUL 3GMC2, which is 1.5 times the Schwarzschild radius.
Photon sphere, what happens there?
Light can actually orbit the black hole there in an unstable circle, like light caught in a trap, just going round and round.
Could you see the back of your head?
Theoretically, yeah. Light from behind you could bend all the way around. It's a wild prediction of GR, which predicts double the light bending compared to Newton. Some light from an accretion disk might even get focused and emerge from this sphere.
Okay, so Schwarzschild is simple, non-spinning. But most things spin. How do we describe a rotating black hole?
That brings us to the Kerr solution, found by Roy Kerr in 1963. This metric describes a rotating black hole. And unlike Schwarzschild, just mass, a Kerr black hole is defined by only two things: its mass, m, and its angular momentum, j, how much it spins.
Just mass and spin.
Just mass and spin. Sometimes we use a parameter a for spin, where at jm it goes from 0 Schwarzschild to 1 max spin. These solutions usually use special coordinates, Boyer-Lindquist coordinates, to handle the math. But yeah, just two numbers describe these complex objects. It's amazing.
And rotation brings back that weird frame dragging. Can you explain that more for Kerr, how spacetime gets dragged?
Yes. Frame dragging is just mind-bending around a Kerr black hole. Inside that ergosphere region, space-time itself is so intensely twisted by the spin that it literally forces everything, even light, to rotate along with it.
Like a whirlpool in spacetime.
Exactly like that. You drop something in, it gets swept along. You cannot remain stationary relative to distant stars inside the ergosphere. You're forced to move with the spin. It's a key signature of rotating black holes, crucial for how they interact with things, like powering jets.
Okay, so spacetime is dragged, negative energy states are possible. Can we actually get energy out of this rotation? It sounds like breaking physics, but you mentioned a process.
Right, it sounds like perpetual motion, but it's real physics. It's the Penrose process, named after Roger Penrose, naturally. It uses the ergosphere.
How does it work?
Imagine a particle enters the ergosphere. It splits in two. One part falls into the black hole, cleverly aimed so it has negative energy relative to us far away.
Negative energy again?
Possible, because space is flowing faster than light in there relative to outside. The other part then escapes back out to infinity, but get this. It has more energy than the original particle started with.
Where does the extra energy come from?
From the black hole's rotation. The black hole sacrifices a tiny bit of its rotational energy and angular momentum to make this happen. It spins down slightly. It's a way to literally harvest energy from the spin.
The black hole powers down to give us energy. Wild.
Does this or anything else tell us about what black holes remember? Like how much info they keep from what fell in?
That leads straight to the no-hair theorem. It's fundamental. It says that black holes, no matter how messy their formation, collapsing stars with chemicals, magnetic fields, weird shapes, end up surprisingly simple.
Simple how?
Once formed, they're described by only 3 numbers: mass m, angular momentum j, and electric charge q, if they have any. All other details, the hair about what made them, is lost behind the event horizon.
Like a cosmic shaver.
Exactly. All that complexity boiled down to just 3 numbers. This simplicity is actually key to some major paradoxes, like the information paradox we'll get to.
Fascinating. Mass, spin, charge. That's it. So we've done non-rotating, Schwarzschild rotating. What about charged ones? Do they exist? Are they different? Well, theoretically, yes. The Reisner-Nordstrom solution describes a black hole that doesn't spin, but does have a net electric charge. It adds another layer of complexity inside.
How so?
Unlike Schwarzschild's single event horizon, these charged black holes theoretically have 2 horizons. An outer event horizon, R+, like usual, and an inner one called the Cauchy horizon.
2 horizons. What's the deal with the inner one?
The outer one is the point of no return. The inner Cauchy horizon is more theoretical, marking a boundary where causality might break down. If you could cross it, the future might not be uniquely set by the past. Very weird territory. There's also a theoretical limit called an extremal black hole, where the charge is maxed out relative to mass, QM. The 2 horizons merge into one. But honestly, astrophysically, charged black holes probably aren't common.
Why not?
Because space is full of plasma. Any net charge on a black hole would quickly attract opposite charges and neutralize itself. So, for real cosmic black holes, the rotating Kerr solution is much more relevant.
Okay, moving from properties to how black holes mess with space-time itself. This is where it gets really abstract. We need different ways to visualize this, right? And you mentioned singularities earlier. Some are just math problems.
That's a crucial point, yeah. Often confusing. The singularity at the Schwarzschild radius, r to gm, in that basic solution, is not physical, it's a coordinate singularity.
Like longitude lines at the North Pole.
Exactly like that. The coordinates break down, but the place itself is fine. To really understand black hole physics and cross the horizon mathematically, we need better coordinate systems. That's where Finkelstein and Kruskal diagrams come in. They give a clearer picture of the true causal structure.
Tell us about the Finkelstein diagram first. How does that help visualize cause and effect, or light rays?
The Finkelstein diagram focuses on causal structure, especially how light rays null geodesics behave. It transforms coordinates so we can smoothly cross the horizon. And what it shows very clearly is that inside the horizon at R for 2GM, outgoing geodesics do not go out.
They just fall inward.
They're irresistibly drawn towards the R0 singularity. Point your flashlight any direction inside, the light falls in. It really drives home the one-way street idea visually. Outward paths just cease to exist inside.
And the Kruskal diagram goes even further, more comprehensive.
Oh yeah. The Kruskal diagram shows the global causal structure of Schwarzschild spacetime. It's amazing because it removes both the coordinate singularity at the horizon and the one at R0, mapping the whole spacetime onto new coordinates.
What does it look like?
It has 4 quadrants. One is our familiar exterior universe. Another is the black hole interior, where everything hits the singularity. But then, surprise, there's an interior of the white hole, mathematically. A time-reverse black hole where things only come out.
White holes.
And even weirder, another copy of the exterior of the black hole, a whole separate universe, mathematically speaking. It's a complete map of all possible pasts and futures for light cones.
Okay, hold on. White holes. Aren't they real?
That's the enigma of white holes. They are valid mathematical solutions from the Kruskal diagram, but they're widely considered to have no physical manifestation in our universe.
Why not?
Because they'd violate the second law of thermodynamics, the one saying disorder, entropy, always increases. White holes would spontaneously spit out matter and energy, creating order from chaos.
Yeah.
That's just not how our universe seems to work. They're math curiosities, not real objects.
Okay, no white holes. But this math also leads to Wormholes, another sci-fi classic. That comes out of these diagrams, too.
It sure does. The Kruskal diagram connects those distinct asymptotic regions, the other universe parts, suggesting a wormhole-like geometry called the Einstein-Rosen bridge.
A tunnel through space-time.
Mathematically, yes.
Yeah.
It connects 2 asymptotically flat regions joined together by a black hole, like folding paper and poking a hole through, a theoretical shortcut.
But the big question, can you travel through it? Interstellar subway.
Crucially, no, not this one.
Yeah.
The Einstein-Rosen bridge is not a wormhole that you can travel through because the paths are space-like, not time-like.
Space-like, meaning?
Meaning you'd need to go faster than light to cross it. Any normal object trying to traverse it would hit the singularity before getting through. It pinches off instantly. It's more like a conceptual bridge than a usable tunnel.
Okay, so no easy space travel. But connecting this to the bigger picture, This geometry plus quantum mechanics leads to really wild ideas, right? Like ER equals EPR. What's that?
Ah, yes. The ER-EPR conjecture. Super fascinating, highly speculative stuff. It proposes a deep link between space-time geometry, the ER, Einstein-Rosen bridge part, and quantum entanglement, the EPR, Einstein-Podolsky-Rosen paradox part.
Entanglement, that spooky action at a distance.
Exactly. The conjecture suggests that maybe two black holes connected by a wormhole, ER, are that way because they're quantumly entangled, EPR.
So entanglement isn't just a correlation, it is a wormhole.
That's the radical idea, that this quantum weirdness might physically manifest as a connection in space-time geometry. People like Susskind and Maldacena champion this. It hints at a deep unity between gravity and quantum mechanics, maybe pointing towards quantum gravity.
Wow. Entanglement literally weaving wormholes. Okay, back to slightly more grounded reality. How do black holes actually form? We talk theory, but what's the real cosmic process?
Right. In the real universe, they mostly form via gravitational collapse, usually the dramatic death of massive stars.
Big stars going boom.
Or rather, imploding. When a star, much bigger than our sun, say 20, 30 times the mass, runs out of nuclear fuel, its core can't fight gravity anymore. The outward pressure stops, and the core collapses catastrophically inward.
And if it's massive enough?
If the remaining core mass is above a certain limit, well, for neutron stars, nothing can stop the collapse. It compresses down, forming a black hole. Sometimes it might be a more idealized, spherically symmetric collapse of a shell of matter, but stellar collapse is the main way.
And this collapse leads to the real singularity and not the coordinate kind.
Exactly. The singularity at Arba 0, where all the mass theoretically piles up, is believed to be a true physical singularity. Space-time curvature becomes infinite, density becomes infinite. It's where classical GR actually breaks down, the endpoint of collapse in Einstein's theory.
Sounds extreme. Does GR allow singularities without an event horizon, a naked one we could just see?
Theoretically, yes. Those are called naked singularities. Singularities not hidden behind a horizon, so their effects can be observed from infinity.
What would that mean?
It would be chaos. Information could escape from a region where physics breaks down. Predictability would be lost. Anything could happen, and we could see it.
So, do we think they're real? Are they out there?
Probably not. The general feeling among physicists is that they're unphysical. This idea is formalized in the weak cosmic censorship conjecture.
Cosmic censorship sounds like a movie rating.
It's a deep idea in GR. It basically conjectures that, starting from realistic conditions, smooth space-time, normal matter obeying energy rules, naked singularities just will not evolve to form.
Nature hides the nasty bits.
That's the intuition. That nature shields us from these breakdowns behind event horizons, keeping space-time predictable for observers far away. The Big Bang singularity is kind of a special case, being more of a boundary of space-time itself.
Okay, so black holes are these dense, invisible gravity wells. But paradoxically, they power some of the brightest things in the universe, like quasars. How does that work if they just suck things in? They don't emit light, right?
That's the key paradox. And the answer lies in the stuff around the black hole. The intense light from quasars, supermassive black holes in distant galaxies, or microquasars, stellar mass ones nearby, doesn't come from the black hole. It comes from the accretion disks which surround them.
Risks of swirling stuff.
Exactly. Swirling masses of gas, dust, plasma, all slowly spiraling inwards, getting incredibly hot as they do.
So it's the infalling stuff that glows, not the hole. How does falling in generate so much energy it outshines galaxies?
It's the accretion process. And it's not just falling straight down. This matter has angular momentum, so it orbits. To fall in, it needs to lose that angular momentum through some dissipative process.
Like friction.
Sort of. As it loses momentum and spirals in, it loses huge amounts of gravitational potential energy. That energy gets converted into heat, immense heat, which then radiates away across the whole spectrum: radio, optical, UV, intense X-rays, gamma rays.
And that light escapes.
Yeah, it leaks out, travels through the warped space-time near the hole, and eventually reaches us. This process is way more efficient at turning mass into energy than even nuclear fusion in stars.
Incredible efficiency. Are all these disks the same? Or do they vary? I've heard terms like thin disks, thick disks.
Oh, they vary a lot. There are different types of accretion disk models for different situations. The classic is the Shakura-Sunyaev thin disk. Geometrically thin like a pancake, radiates heat away very efficiently. Good for moderate accretion rates, often stops at the isotope.
Okay, thin disks. What else?
Then you have slim disks. They're thicker, can handle much higher accretion rates, near or above the Eddington limit where radiation pressure starts pushing back.
Yeah.
In slim disks, heat gets carried inward with the flow. advection, as well as radiated, so they don't necessarily get infinitely brighter.
And at low rates.
At very low rates, you get advection-dominated accretion flows, ADFs. Very hot, but optically thin, transparent, and geometrically thick, like theoretical Polish donuts. Most heat gets sucked into the hole, not radiated, so they're quite dim, even though they're hot.
Like our own SGRA.
Exactly. SGRA is surprisingly dim, likely an ADF. These models help explain the huge range of observed black hole brightness.
Makes sense. So this energy release depends on shedding angular momentum via some dissipative process. What is that process? Just simple friction seems too weak.
Right, that's the viscosity problem. Ordinary molecular viscosity, like stirring honey, is way too weak to move angular momentum outwards fast enough to explain observed accretion rates. So the main mechanism must be turbulence.
Chaotic swirling motions.
Yes, like in a fast river. But what drives the turbulence? That was the next puzzle.
And what's fascinating here is the answer involves magnetic fields, doesn't it? They're absolutely crucial.
Profoundly crucial. The breakthrough was understanding the magnetorotational instability, or MRI, also called the bulbous-Hawley instability.
MRI. What does it do?
It shows how even weak magnetic fields inside a disk can tap the sheer energy of its differential rotation to power turbulent fluctuations.
Sheer energy. From spinning at different speeds.
Exactly. The inner disk spins faster than the outer disk. Magnetic field lines linking these regions get stretched and twisted, amplifying the field and driving instability, creating strong turbulence.
And that turbulence moves the angular momentum.
Precisely. It leads to angular momentum transport and energy dissipation, exactly what you need for accretion to happen efficiently. Without MRI, accretion disks wouldn't work nearly as well. Plus, strong magnetic fields can also launch those powerful jets we see.
Okay, so MRI drives turbulence, heats the disk. How does that heat get out as radiation we see? What are the main ways?
Two main dominant radiation processes in these hot, dense environments. First is Bremsstrahlung, or breaking radiation. That's when fast electrons get deflected by ions or other electrons, and they emit photons as they slow down or change direction.
Okay, breaking radiation, what's the other?
Comptonization. Here, hot electrons collide with lower energy photons already floating around, maybe from Bremsstrahlung or synchrotron radiation. The electrons upscatter the photons, giving them a kick of energy.
Making them higher energy.
Yeah, turning lower energy photons into higher energy ones, like X-rays. It's like the hot electrons are playing billiards with photons, transferring energy.
So we have these incredibly complex systems, disks, magnetic fields, turbulence, radiation relativity. How do scientists even model this?
That's where numerical simulations are absolutely key. Modern, relativistic MHD, magnetohydrodynamic simulations, magnetohydrodynamics, basically modeling electrically conducting fluids like plasma interacting with magnetic fields, and even more advanced, radiation MHD plus gravity simulations.
What do they capture?
They try to capture the true dynamics of the disk, how matter flows, fields evolve, energy moves, radiation escapes, all while dealing with the black hole's intense gravity. They're crucial for understanding how jets are launched, how energy gets extracted.
Do they always need to include radiation?
Not always. For dim sources like SGRA, sometimes you can ignore radiation's effect on the flow. But for brighter objects, accurately modeling heating and cooling is critical. Different assumptions there can lead to very different simulation results.
Okay, here's where it gets really interesting for me. Beyond the steady glow, sometimes we see these incredibly precise rhythmic flickers from these systems, quasi-periodic oscillations or QPOs. What are they, and why are they so vital for probing extreme gravity?
Quasi-periodic oscillations, QPOs. Yeah, they're amazing. They are strikingly regular patterns buried in the noise of the light curves from black holes and neutron stars.
Light curves meaning brightness over time.
Exactly. Plot the brightness. And amidst the random flickering, you find these subtle but persistent rhythms, usually very fast, hundreds of hertz for black holes in our galaxy, like hundreds of cycles per second, like cosmic humming.
Hundreds of times a second. How do these rhythms help us understand strong gravity?
They are maybe our best tool for probing strong gravity. QPOs give us a way to test GR and its strong field limit, right near the black hole, just a few gravitational radii away, where space-time is most warped.
Closer than we can usually see directly.
Much closer. Techniques like VLBI might eventually image that region for supermassive black holes, but for stellar mass ones, QPOs are a more practical approach right now. They're like listening to the heartbeat of space-time right near the edge.
And their stability is key, right? It tells us something fundamental about the black hole itself.
That's the real kicker. The incredible stability of observed QPO frequencies over very long periods of time. For example, the microquasar GRO-J665540 showed QPOs at 300 Hz and 450 Hz in 1996. And then almost 9 years later, in 2005, it showed the exact same frequencies.
Wow, 9 years apart, same frequencies.
Yeah. This strongly suggests the frequencies cannot depend on quantities such as magnetic field, density, temperature, or accretion rate, because those things change wildly over time.
So what do they depend on?
They must depend only on the mass and the spin of the central black hole, the fundamental, unchanging properties of the spacetime itself. This directly links these precise oscillations to extreme gravity, making them a unique laboratory for testing GR and maybe even measuring black hole spin.
We've covered the basics, detection, properties, how they act as engines. Now let's push into the really weird stuff, the frontiers where black holes challenge physics itself. We mentioned the Penrose process for getting energy out. Can you expand on that and how it ties into fundamental black hole laws?
Right, the Penrose process. It's a brilliant illustration of tapping the rotational energy of the black hole. Remember, a particle enters the ergosphere, splits. One part falls in with carefully arranged negative energy relative to infinity.
Because space is flowing faster than light there.
Exactly. The other part escapes with more positive energy than the original particle had. The energy comes directly from the black hole's spin, causing it to spin down slightly.
And this connects to a bigger principle, a kind of conservation law for black holes.
Yes, it connects beautifully to the area theorem, or Hawking's area theorem. This states that the area of the black hole's event horizon always increases in any physical process, or, at best, stays the same. It never shrinks.
How does the Penrose process fit?
When the Penrose process extracts rotational energy, the black hole's mass effectively drops a tiny bit. But crucially, its surface area still increases or stays the same. This means you can't use the Penrose process to spin a black hole down so much that its horizon disappears, which would create a naked singularity.
So the area theorem upholds cosmic censorship.
In a way, yes. It acts as a safeguard. And this constant increase in area looks remarkably like the second law of thermodynamics: entropy always increases. That analogy was a huge clue that black holes might have entropy.
Okay, so particles can steal energy. Can waves do it too?
Yes. There's a more general version called superradiance. It's like a grown-up version of the Penrose process. Incoming waves, light waves, gravitational waves, quantum fields can scatter off a rotating black hole inside its ergosphere and return amplified.
They bounce off with more energy.
Exactly. They steal rotational energy from the black hole. Imagine sending a wave at a fast-spinning drum. It could bounce back stronger. For a black hole, the wave interacts with the frame-dragged spacetime and gets amplified. It's another way black holes can lose energy and spin over time.
Truly wild. But maybe the biggest, most famous puzzle is the black hole information paradox. What is this huge challenge that pits our best theories against each other?
The information paradox. It's a massive, unresolved conflict between our two pillars: quantum mechanics, QM, and general relativity, GR.
What's the conflict?
QM insists that information, the complete quantum description of something, can never be truly lost from the universe.
Yeah.
It's a core principle called unitarity. Evolution is reversible.
Okay, information can't be destroyed in QM.
But GR, combined with Stephen Hawking's prediction of Hawking radiation, the idea that black holes slowly evaporate by emitting thermal radiation, seems to say information is lost.
How so?
Because a black hole eventually evaporates into seemingly random, featureless black body radiation. This thermal radiation supposedly carries no information about what fell in. If you throw a book into a black hole and it evaporates into heat, where did the information in the book go? It seems destroyed. That violates QM. That's the paradox.
And Hawking himself, who proposed information loss, later changed his mind. That's huge.
Absolutely huge. Hawking famously argued information was lost. But in 2004, after decades of debate and work by others like Turft and Susskind, he conceded that information is preserved in black hole evaporation. A monumental shift.
So consensus is information is saved. But how?
The consensus leans towards preservation, yes.
Yeah.
But how is the multi-trillion-dollar question? One leading idea is the holographic principle.
Holographic, like on a credit card.
Kind of. It suggests that all information about what falls into a black hole isn't lost in the volume, but is somehow preserved on its surface area, the event horizon, like a 3D reality encoded on a 2D surface.
So the history is written on the surface.
That's the idea. It's radical, even suggesting our whole universe might be like a hologram projected from a distant boundary. It's a potential path to linking gravity and quantum mechanics, born from black hole physics.
But even with Hawking changing his mind and ideas like holography, it's still not solved.
No, not fully resolved. Physicists still disagree on precisely how Hawking's original semi-classical calculation should be corrected to show information getting out. It remains an active field of research in quantum gravity, pushing physics forward, forcing us to figure out how gravity works at quantum scales.
This drive for unification seems central. How does information preservation affect Hawking radiation itself if it's not just random heat?
Exactly. If information is preserved, then Hawking radiation can't be purely thermal, purely random noise. It must somehow, subtly, be encoded with the information of what fell in.
So the radiation isn't featureless.
It can't be, if QM holds. This forces us to understand quantum fields near horizons in a much deeper way. The outgoing radiation must somehow reflect the black hole's internal quantum state, allowing information to escape as it evaporates. How that happens is the core mystery.
And this all ties back to thermodynamics. You mentioned entropy. How do black holes fit into heat and disorder? Seems weird.
It was weird, but it's revolutionary. Black hole thermodynamics pioneered by Bekenstein and Hawking. The key is the Bekenstein-Hawking entropy formula, SPH, C3A4G.
Entropy is proportional to area.
Directly proportional. The area A of the event horizon is its entropy, SPH, up to some fundamental constants. This means black holes aren't just cold endpoints, they're thermodynamic systems with temperature and enormous entropy.
And the area theorem fits this. Area always increases.
Just like entropy always increases. So that area theorem becomes part of a generalized second law of thermodynamics for the universe. Total entropy, normal stuff plus black hole area entropy, never decreases. It forces this incredible unification of gravity, quantum mechanics, that in the formula, and thermodynamics.
So black holes are forcing this unification. What are the main paths scientists are taking towards a quantum theory of gravity to solve these puzzles?
It's the ultimate quest. Several approaches are being explored. String theory replaces point particles with tiny vibrating strings, hoping gravity emerges naturally from their interactions.
Okay, string theory. What else?
Non-commutative geometry messes with spacetime itself, suggesting coordinates don't commute at tiny scales, blurring location. Then there's canonical quantum gravity, trying to quantize GR directly, with loop quantum gravity being a major example. Interestingly, GR itself was kind of the first non-abelian gauge theory, predating Yang-Mills, hinting gravity is deeply linked to other forces.
So different ways to quantize gravity. Are there even more radical ideas about gravity itself inspired by black holes?
Yes, some very different perspectives. Like the Sakharov idea. It suggests gravity might result from quantum field theory, not be fundamental itself.
Gravity emerges from QFT.
Yeah, viewing gravitons not as fundamental particles, but as collective excitations of a cold quantum liquid. The vacuum of particle physics, like sound waves emerging from atoms. Gravity is an emergent phenomenon. It shows how black holes force us to question everything about space-time and reality.
What an absolutely incredible journey today. From Einstein's doubts to Penrose's proofs to Genzel and Gez actually seeing their effects.
Yeah, navigating event horizons, ergospheres, ICOs, seeing how space-time drags, how energy can be stolen.
And then peering right to the edge of physics with the information paradox, seeing black holes connect gravity, quantum mechanics, thermodynamics.
They really are the universe's ultimate laboratories, forcing us towards a unified theory, helping us understand the Big Bang, the ultimate fate of things.
So what's the takeaway for you listening? Considering how these cosmic prisons, black holes, are paradoxically giving us the deepest clues about quantum mechanics, thermodynamics, reality's fabric, it makes you wonder, doesn't it? What other unbreakable laws might just be waiting to reveal deeper truths, waiting just beyond the event horizon of what we currently understand?
The universe is definitely full of questions, and black holes are right at the frontier of finding answers.
We really hope you'll keep pondering these mysteries. Maybe do your own deep dive into this ongoing, thrilling quest for a theory of everything, a quest where black holes are leading the charge.